All right, now I want to spend some time talking about a concept known as dimensions. The word dimensions has many different meanings in physics. The particular meaning that I want to talk about now is referring to the kind of quantity that we are measuring. So there are many different kinds of quantities we might wish to measure in physics. For example, we might wish to measure lengths. Okay, how far is it between 2 points? How long is my ruler? We may wish to measure mass. That's not really how heavy something is, but how much stuff it has in it. However, that is very tightly related to how heavy the object is. And lastly, time. How much time passes between one event and another? Or how long do you have to wait for this lecture to be over? So those are the three fundamental quantities we will be measuring. However, there are other quantities we can measure that are combinations of these different dimensions. For example, if I want to measure a speed, well, when you drive on the freeway, you know your speed is measured in miles per hour. Well, that's a distance, a length, miles, divided by a time, hours. So speed, in fact, is measured in length over time. Now this is a cute little Far Side cartoon where the lady here has just helped clean off Einstein's desk as Einstein is struggling to figure out his E equals mc squared equation. And she says, wow, that desk sure looks better. Everything's squared away. That's right, squared away. And of course, Einstein realizes, aha, it's E equals mc squared. Well, that's not really how it would have happened, and Einstein, being a big physicist, would have known that c squared was the only option he had. And here's why. Energy has units, or dimensions. Dimensions of energy are mass, length squared, over time squared. Mass, length squared over time squared. Well, if E equals mc to some power, well, mass is a mass, and c is a speed, which means it has dimensions of length over time. So the only way to get the right dimensions for E is going to be if I choose c to be squared. That is the only option that will give me the correct dimensions for the energy. That's a really good predictor. It helps us to know whether or not our equations can be right, and it helps us to make predictions about what the right form for an equation is. So here's a prediction. Your first test will have at least one question of the following type. We've got a particular situation where we're measuring a distance, x, and relating it to time. And we know it's related by an equation that says x equals k at squared. And the question is, if k is a dimensionless constant, what are the dimensions of a? Well, we know that the dimensions of x are length, and the dimensions of time squared are time squared. K is dimensionless, so all I'm left with is that the dimensions of x had better equal the dimensions of a times the dimensions of time squared. But that means length is going to equal the dimensions of a times the time squared, so the dimensions of a had better be length over time squared. That is the only option that will give us the right results. Now, I made a prediction that you'll have a problem of this type. It is possible that the problem could run the other way around. In other words, you may be asked whether or not an equation is correct, or could be correct based on dimensions, where you have to look at the dimensions of both sides of the equation and make sure they agree. Remember, the dimensions on both sides of an equation have to always be the same, and anytime you're adding two things together, they have to have the same dimensions. That's not true when you multiply or divide. You can multiply and divide things of different dimensions. But if you add them, subtract them, or put them opposite each other on an equal sign, they must have the same dimensions.